Hello, my name is Roy Simpson. I'm a professor of mathematics at Kissimmee River College in Sacramento, California. This is going to be part B of the lecture on slope for intermediate algebra. In this part, we're actually going to just talk about slope as an introduction, talk about kind of the idea of slope mathematically, and maybe do a few problems. Now, if you just finished watching part A of this lecture, then you know that just from that, one of the problems we did there, that slope is defined to be the change in elevation divided by the change in horizontal position. Some people would also say this is just the ratio of change in elevation and change in horizontal position. And if you think of that visually, we have some change in elevation, and in mathematics we use the Greek letter capital delta. It looks like a little triangle actually, to denote a change. So change in y, we'll just say this is the y direction, up and down, over change in horizontal position, and we'll just pretend that horizontal position is denoted by x. So there's change in y over change in x. So let me go ahead and say this is like change in y over change in x. So maybe I should say this is like the first definition. Here's the second definition. There's a ton of definitions of ways to think about this. They're not really definitions, but just ways to think about this. Another way to think about this, which students often love, is the fact that you have this change in elevation. We call that a rise. And the change in horizontal position, a lot of students call the run. So they say it's rise over run. All right, I'm kind of willing to agree with that. Another one to kind of chew on is my preference, which is change in output over a change in input. And the reason why I like this one actually is because later on in mathematics, this idea of output and input really defines a whole new structure within mathematics called a function. And so I often, if you think about a graph where maybe the x-axis represents, or the horizontal axis maybe I should say, represents the number of years you've worked at a job, so time, and the y-axis represents, or I'm sorry, the vertical axis represents your salary. It could look something like this, right? And the vertical variable is what we would get as an output if I plug in a different year. So if I plug in this year, I have an output. If I plug in next year, I have a different output for my salary. So I consider the horizontal variables the inputs and the vertical variables the outputs. Well, if the vertical variables, the up-down variables, are output, well then the change in up-down, or the change is the same thing as the change in output. And the change going left right, or in horizontal position, is the same thing as saying change in input. Not necessary that you know this right now, but still a very nice way to think about it. All these are equivalent. So for an example, let's go ahead and compute the slope of this line right here. And if you look at this line, it goes through a couple points that are pretty easy to see. It goes through x equals 0. I'm sorry, not x equals 0. X equals 4, y equals 0. And it goes through x equals 0, y equals 3. All right. So remember, the slope has a bunch of different definitions. Rise over run, change in elevation over change in horizontal position. Any of these are equivalent. So let me take the rise over run idea. And I'll tell you why the rise over run idea is kind of difficult sometimes. If I want to find the slope of this, I'll start anywhere I want on the line. And in fact, it's just very nice to start at this beautiful little y-intercept right there. And I'm going to go only up, down, and left, right to get back to the line. In other words, I'm going to go ahead and drop down few steps here. Maybe I should make my pen width a little bit thicker so that you can, maybe a lot thicker actually, so you can see it. Drop down and then move over until I get to here. Well, how many steps was that in which directions? Well, let's see here. In the vertical direction, I went down 3. Well, down 3 means negative 3. So remember, slope is change in elevation or change in output or change in vertical variable or change in rise over run. Well, our rise was actually a negative 3. We went down 3. And then once we went down 3, to get over to this next point, we went a few steps this way, right? Point little arrows right there. We went over 4. And we went in a positive direction 4. Remember, right is a positive direction. So we went over a positive 4. So we ran a positive 4. The slope of this line ends up being a negative 3 over 4. What's interesting about this is that you could actually have taken any other point on this line, any other 2 points on this line, and computed the slope, and it would actually be the same slope. We'll investigate that in a little bit, but let's just go ahead and try a few more problems where we can find the slope of lines. Let's take, for example, this one. Let's compute the slope of this line. And I'll go ahead and highlight a couple points that are kind of easy to see here. This looks to be x equals 0, y equals a negative 12. And this looks to be x equals 10, y equals 0. Again, I'm going to go ahead and mark out a path here. So I'm just going to choose a point to start, and really this point right here is the easiest point to kind of start from. I'm going to go up until I get to a nice easy point, and I'm just going to say that that's an easy point because from here I can go over to the right to get to this next highlighted point. So when I did that, when I went up 12 units, and then from there I'm going to go over 10 units. Now up is positive, and I went over in the positive x direction, so it's positive 12 over positive 10. So let me go ahead and write that down. The slope, which again is, a lot of students like to say rise over run, or change in y variable over change in x variable, is up 12 and over 10. Now, this is not proper to leave it like this. Whenever you have a fraction, you should always reduce it. Those are both divisible by 2, so that would be 6/5. That would be the slope of this line. Now let's try something that's slightly different. Instead of starting with a graph, let's just start with a couple points. Because really on the graphs, that's all we're doing as well. We're just starting with some points. So in this case, we're asked to compute the slope of the line going through these 2 points. And just remember that the slope is just the same thing as rise over run, or in other words, change in the y value over the change in the x value. Well, let's see, the change in y values. Now, I'm not going to draw a line going through those points. I'm just going to draw a random line here. If I want to know what the change in the y value between these 2 points is, let's just pretend that the first point is called x1 comma y1, and the second point is called x2 comma y2. If I want to find the change in the y values here, I would say, well, it's the top y value minus the bottom y value. Let's pretend the top y value is 10 and the bottom y value is 3. While it's not what it is on this graph, let's just pretend for a moment that the top y value is 10 and the bottom was 3. Well, then the distance between them would be 7, which is 10 minus 3. So you're essentially saying that the change in y is going to be y1 minus y2. Along the same lines, since we started with this point here at y1, which we could call point 1 if we want, then the change in the x variable will also start from here. It will go from x1 to x2. So in other words, get that. Now, a lot of people, in fact most people, like to write it the other way around. They like to write it as y2 minus y1 over x2 minus x1. I don't really care which way you write it, except that where x2 is, y2 should be right above it. Where x1 is, y1 should be right above that. Okay, that's extremely important. So in our case right here, the slope of this equation, or I'm sorry, of the line going through those 2 points, will be y, the difference in the y values. And what I'm going to do is go ahead and call this y2, so this must be x2. And I'll call this y1, so this must be x1. So it'll be y2 minus y1 all over the difference in the x values, which is 4 minus the x1 value, which is a negative 7/2. Be very careful. A lot of students tend to forget about the fact that you're subtracting a negative. Subtracting the negative becomes a positive. So this is going to be 19/2 minus 3 all over 4 plus 7/2. This is a complex fraction. Recall from elementary algebra, that in pre-algebra actually, that you can multiply top and bottom of an expression or a fraction by any number you want that's non-zero. So I can multiply top and bottom of this by any number I want, and I choose to multiply top and bottom by the number 2. Just because I know that when I distribute this 2 to each of these objects, it will cancel at least the fractional pieces. So we get something like 2 times 19/2. Well, the 2's cancel, so that's just a plain old 19 minus, and then 2 times 3 is 6. 2 times 4 is 8 plus 2 times 7/2 is just 7 because the 2's cancel. And this is equal to, doing the little PEMDAS here, right? Work upstairs first, so you get 13 up there and a 15 in the denominator. So the slope of this or of the line going through these 2 points is 13/15. Now, one last little thing before I finish this lecture, and maybe I'll also include a little bit of an animation at the end of this lecture and at the beginning of the next one, is that the slope, we often use a letter to denote the slope. It is change in y over change in x, but a lot of people call the slope m. And that's derived from a French word for mountain, actually. And I'm going to butcher it. I think it's Montier. And that's where the m is derived from. So m stands for slope. So when people say, oh, m is equal to 13/15 in that last problem, they're saying the slope is equal to 13/15 in that last problem. So far what we talked about mathematically is how to figure out how steep a line is. That's all we've done. Now, before we finish up this video lecture, I want to take you here to, this is a Mathematica demonstrations project. The Mathematica, or the Wolfram's demonstrations project, can be found by just Googling Wolfram, that's WOLFRAM, demonstrations project. And then you can find all these demonstrations, and there's a plugin that's free to use that you can go ahead and download, and you can play with this stuff. And essentially what it allows you to do is view what the slope of a line through 2 points is. So like this line goes through -2, 2 and 2, -1. And notice that it already calculates the slope as -3/4. If I grab the point and start moving this point, you notice that the line itself, the blue line, as I increase this, sorry, there's a dog outside. As I increase this, the line gets steeper and steeper, right? It looks like it gets steeper and steeper, but notice it's still a negative number. Now, something else you should note is that as I get less and less steep, the number's still negative, but at some point it becomes 0. Notice that the slope of this line, it's just a flat line. Well, when you have a flat line, the slope is 0. And now if I increase it, now notice the slope is positive. And the more I increase the slope, or the more I increase the steepness of it, the slope actually will get larger and larger. There's a slope of 7 right there. Okay. So what's interesting about this is that a horizontal line has slope 0. If the line is increasing from left to right, the slope is positive. You're climbing that mountain. And if the line is decreasing from left to right, it has a negative slope. In other words, you're falling down that mountain. So let me write that, and then we'll call it quits on this one. So a line with a 0 slope is horizontal, and it also works the opposite direction. A horizontal line has a 0 slope. Oh, I forgot my end parenthesis there. Another thing that we mentioned there is if the slope is positive, that in other words, that m is greater than 0, then the line is increasing from left to right. If the slope is negative, in other words, that m is less than 0, then the line is decreasing from left to right. Okay, that's all I'm going to talk about as far as the introduction to slope. Quite a bit to kind of digest there. However, we will, in the next part of this lecture, go into more detail on the slope.